Hi, my name is Sonia Nusser. I use she, her pronouns, and I am the chair of the Women in Science and Engineering Club. We do lots of events. We host an annual symposium, which you are at right now. Most years it's in person, but for obvious reasons, not this year. And then we also host guest speakers, and occasionally we take like field trips to go visit. For example, we once went and visited some labs at the University of Oregon and went and saw the ant farm in the basement of the volcanology building. Super cool. So yeah, if you're interested in any kind of STEM, math, engineering, we would love to welcome you. We're open to everybody, and yeah, love to have you at a meeting.
Thank you. So without much further ado, I am going to introduce to you Miss Rebecka Tumblin from UO. She is a UO doctoral candidate in science, and she is also an instructor at Oregon State University. So I am going to let her introduce herself and tell you a little bit more about how she got to where she is, and then she's going to talk about her research in astronomy. Welcome, Rebecka.
Thank you. Well, hi, everyone. My name is Rebecka, and I would like to talk to you today about what I've been up to for the last several years in school. Okay, so let me share my screen real quick, and I'll present to you guys some cool stuff that I've been doing. Okay. Okay. So first, a little bit about me. Well, I graduated from college with a bachelor's degree in 2014. Okay, so since then, I have gone on to continue my post-bachelorate education, and I've earned a master's degree, and now I'm doing novel research at the University of Oregon on star formation and planet formation. Now, going to college was a really exciting thing for me because I grew up in a very low income home and there was not money for me to go to college. And my family didn't really push me to go to college either. So when I graduated high school, I went and got a job and worked for about 10 years doing various different things. So going to college was a special experience for me. And since then, I've gotten to do some other pretty cool things like work at different telescopes, do various different research. And I don't know if you've ever gotten to sit in the dish of a telescope, but you can if you would like to. You just have to pursue dreams of science like I did. Okay? So what I'd like to talk to you about is what do I actually do now? What do I do now that I have graduated? And really, what does a scientist do? Okay, so what do I actually do? Well, let's just review a little bit. First of all, what is science? Okay, what exactly is science? Okay. Well, I'm sure you've learned in your science classes that science, well, is an iterative process, right? It usually involves making some observation about nature and questioning why this happens the way it does, and then trying to answer that question by forming a hypothesis, gathering data, testing your models, modifying and going through this process over and over and over again. So really, what science does is it seeks to explain natural phenomena through purely natural causes. Okay, so this means no mythology, no divine intervention. Astrology is not going to answer the questions of why planets form. Okay, so really, we want to explain natural phenomena naturally. And we want to make models of nature that explain these observations as simply as possible. Okay. This is sometimes called Occam's razor, or the principle of parsimony. Okay, so if you are presented with multiple different hypotheses which could explain some phenomena, you should always pick the one with the fewest possible assumptions. So the simplest answer is usually better than a very complicated hypothesis. And a scientific model, right, must make some kind of testable predictions. And if it cannot stand up to testing, right, we must either abandon this model or revise the model. So what I'd like to present to you today is a model for planet formation in multiple star systems. So I heard that you have just finished your exoplanet module in class. And so you have probably seen that there are now thousands of planets that we've discovered that are not in our solar system. And it turns out that several of these planets come in very strange planetary systems that are not like ours at all. Okay? And some of these planets actually orbit around more than one star. So there are two stars, two suns in the sky for these planets. And basically what I'm trying to do is understand how these planets can form. So let's talk a little bit about the basics of star and planet formation. So all stars and planetary systems that we know of form from the material that makes up these giant molecular clouds. And this is an image of a giant molecular cloud that has broken off the Carina Nebula. This image was taken by the Hubble Space Telescope. Okay. And sometimes this particular molecular cloud is nicknamed the finger of God because of its suggestive shape here. Okay. And this molecular cloud spans about 2 light years in length and about half a light year in width, okay, at its widest part here. And these red stars that you can see are newly formed stars. Okay, so these are baby stars, and they are shaping this molecular cloud with their stellar winds. So how exactly do stars form from all of this material? Well, star formation is really also an iterative process. Okay? So our current model of how stars and planets form is called nebular hypothesis. And nebular hypothesis states that, well, we have these giant molecular clouds. Okay? Gravity will help coalesce material within these clouds. Okay? And if we can get a balance between gravity and pressure, or I should say an imbalance, okay, then part of this material will start to collapse under its own gravity. And as it collapses, nothing in space is stationary. And so it has some rotation. Right? And as it collapses, it spins faster and creates a protoplanetary disk. So this would be our protoplanetary disk, okay, here. And what we have is we have a central star-like object surrounded by a disk of material from which planets will form. Now, this is very similar to what you see around Saturn, just on a much larger scale. And eventually, usually within about 1 to 10 million years, okay, planets will form. The star will begin to fuse materials together to make energy. Okay? And then once the star has burned through all its energy, right, it goes supernova and releases its guts back into space. And this process starts over and over again. So this model explains how single stars form, but it does not explain how binary stars form. So, and is there evidence for this model? Do we have solid evidence that this process actually happens? Can we observe protoplanetary disks? Well, the answer is yes. Okay, so this is the Orion Nebula, and this is another Hubble image of a star-forming region within the Orion Nebula. Okay. Orion Nebula, if you know the Orion constellation, right, this is in his belt. Okay. So all of this is going on right here in Orion's belt. Okay. And if we zoom in to small little areas, we can see these protoplanetary disks at various different orientations. Okay. And this image was taken about 15, 20 years ago. And we can't really see very much detail from this image. And it's taken a long time for our telescopes to become modern enough to be able to see actual details in these disks. But now, just in the last 5 years, with a very special telescope in the Atacama Desert in Chile called ALMA, have we now been able to image details of these protoplanetary disks in various stages of their formation. So here we have HL tau, and you can see that there is a dense stellar object in the center. And these dark lines are believed to be places where planet formation is going on. So we have protoplanets in this disk that are starting to sweep up the material so that they can form into fully fledged planets. And we see disks that come in various shapes, various sizes, and with various different properties. This disk, LES 227, has these notable spiral arms. Now, interestingly, we know that galaxies form spiral arms, but it turns out that during the formation process of planets, we also see spiral arm features happening in protoplanetary disks. So these kinds of images have only been possible in the last 5 years, and this helps us constrain theories of how planets form. So with more observational data, we can better modify our theories about how star and planet formation happens. So this is just an image, a mosaic of many, many different protoplanetary disks that we've imaged in the last few years. And we see that many of them have this gap structure, okay, where there's these gaps in the rings, okay? And just like moons in Saturn's rings can shape those gaps, okay? Well, so can planets shape the gaps in a protoplanetary disk. So, well, that's a brief overview of how we believe that solar systems form, okay? But what about all these exoplanets that you've been learning about in your class? Okay. So we've now discovered 4,390 exoplanets in a little over 3,000 planetary systems. Okay. And it turns out that this is a very exciting time for astronomy. 20 years ago, we didn't know that there was any other planets besides the ones we had seen in our solar system. At least there was no confirmed evidence. Many scientists believe that pretty much every star harbors planets, but we didn't have any actual evidence to prove that. And now we do. And it seems that every single star that we look at, if we look long enough and hard enough, we find planets around it. So this is a very exciting time. So as a scientist, I wanted to try and understand more about these exoplanets. So I made a scatter plot of all the planets that we've found so far. And how I plotted them was based on their mass. Okay, so we have mass on this axis, okay, increasing as we go in this way. And I've made my scale in terms of Jupiter's mass. Okay. So here at 1, we have 1 Jupiter mass. Okay. And on my other axis, I plotted the distance from their parent star or their primary star. Several of these planets orbit more than 1 star. And I noticed something really, really interesting. Oh, sorry. And the separation distance from their star is measured in astronomical units. Okay? So Earth sits at 1 astronomical unit away from our parent star. Our parent star being Sol, the one that greets us every day. And so I noticed something very interesting when I started to plot the planets in this way. I noticed that there were 3 distinct groups, right? And there were areas in between where there were sparsely populated planets. And then another very interesting thing is I plotted the planets in our solar system. And it turns out that we are outliers in this scatter plot of the various exoplanets that we found. So there are several conclusions that we can make. And one is that there's probably many planets that we haven't discovered yet that fall somewhere on this graph. And possibly the way that we observe these planets is affecting why we see only certain types of planets right now. Or there is some mechanism at work in nature that favors these areas for making planets. So currently, I don't have any conclusive way of saying. We will have to gather a lot more data before I can say which of those is correct. But it's an interesting idea to keep in mind. So here's Jupiter. And so I also started to look at some various properties of these groupings that I found. So over here, these planets that I've highlighted in red are planets called hot Jupiters. And these planets are orbiting dangerously close to their parent star. Okay? Remember, Jupiter, our Jupiter, is kind of out here. Okay? And so these are very close to their planet, to their sun, to their star. Okay? This would be where Earth's orbit is. Okay? And so this would be like having Jupiter in Mars's in Mercury's position. Okay, so these are gas giants that are boiling. They're just super hot. Okay? Another grouping of planets that I was interested in were planets around binary star systems, okay, orbiting more than 1 star. And it turns out that these planets I've highlighted in blue really tend to be high mass, okay? And they tend to sit in those upper 2 groupings that that I made. Okay? And we don't really see very many of them in these little rocky planets, this little rocky planet grouping down here. sorry. I'm not able to use my, hang on. I am not able to use my mouse. There we go. All right. So these binary planets are very interesting. This is a image from the first Star Wars movie where Luke Skywalker is on his home planet of Tatooine. And they pan over in the movie and you see that there are actually two suns setting in this scene. Okay, and so these planets around binary star systems could be something like this, where you could see two suns setting in the sky. However, the planets that I've noticed tend to form around binary star systems are not rocky planets like Tatooine. They're big gas giant planets like Jupiter. Okay? And so I really wanted to understand how we could form planets like this, because currently there is no theory that would explain the formation of a planet around a binary star. So to kind of summarize, it turns out that about 45% of all stars that are the same type as our sun, okay, occur in binary or multiple star systems. Okay, so this is an observation that we've made. Okay, and only recently have we observed binary stars in the early stages of formation. Okay, so here is a protoplanetary disk with a forming binary star. Okay, this image came out only a couple years ago, and it's often called the cosmic pretzel. Okay, and it is a binary star system surrounded by a double planetary disk. Okay, circumplanetary disk. So now comes that time in the scientific method where I have to make a hypothesis and I need to test that hypothesis. So what I did was I did a lot of research on what has been done so far. And it turns out that there was this very interesting experiment where astronomers and astronauts actually went into space and they spun drops of water. And once they got them spinning, it turns out that these drops of water would form these interesting shapes, and then we could get a bifurcation. And I thought, I wonder if we could spin up a star fast enough so that it could bifurcate and create a double star. And it's already been shown that the material from which stars form can be modeled like a fluid. Maybe not water, but still a gaseous fluid. And so from this observation that 45% of all solar type stars occur in binary or multiple star systems, okay, I wanted to know, how do we create close binaries and how can we form planets around binary stars? And so my hypothesis is, well, possibly rapidly rotating initial protoplanetary disks, okay, could cause a single star to bifurcate and create a double star. And so how can I test this hypothesis? Astrophysics is very difficult in this way because, well, I can't really go to a lab here on Earth and create a binary star system, okay? Also, these planetary systems take between 1 and 10 million years to evolve, so I would never be able to observe this whole process in my lifetime. So how can I test this hypothesis? Well, it turns out that there is a new emerging field in astrophysics called computational astrophysics. And so, warning, big scary math here. I learned how to speak this very beautiful mathematical language while I've been in college studying physics. And I made a very simple assumption. let's combine hydrodynamics with the basic laws of conservation of mass, conservation of momentum, and conservation of energy.
Excuse me, Rebecca.
Yes.
There's a couple of questions. If we could just break in for a moment.
Yes.
One is, can you explain what is it bifurcate?
Oh, yes.
means?
Bifurcation. Sorry, this is usually when one thing splits into two. So here we are looking at a single drop. It starts to rotate. We can get it to rotate faster in space, okay? And it goes through these different shapes, ellipsoidal shapes. And then once it separates into two, we call that a bifurcation.
Thank you. Thank you.
Are there other questions?
There is one more. I think, Elizabeth, you have one?
Yes, it applied to the charts you were showing earlier.
Okay.
And it was, is there a reason that the data shows most of the planets are really close to their home star?
You mean these hot Jupiters?
Mm-hmm.
Okay, so this is not necessarily most of the planets. It's just one particular grouping of planets that we have found. And really, I was trying to hint at there is probably observational bias going on here. Okay, so the way in which we can observe planets around other stars tends to allow us to see certain types of planets. Okay, so particularly these hot Jupiters that I was talking about are usually found by watching if the star wobbles. Okay, so as the planet orbits the star, the planet doesn't necessarily orbit the star. They both orbit a common center of mass. Okay, so the star is just much, much bigger, so it doesn't move very much. Okay, and so these particular planets were mostly found by looking for that wobble in the parent star. Does that answer your question?
Yes, I think so.
All right. Okay. So, big scary math, okay? And then what I do after this is, well, I turn all this big scary math into computer code, okay? And I simulate the formation of a star system using a computer. Okay? And what I did was I ran these models on the supercluster, the supercomputer at the University of Oregon, and they ran for about 2.5 years of me going through this formation of these protoplanetary disks and star disk systems. And what I get out is images, okay, or images. I can make images of the mass distribution, okay, how this mass, how this astrophysical fluid evolves in time, okay? And this is an image of one model that I ran, okay, that formed a binary star system. And we had some of these spiral arms coming off. So does this match observation? Okay. Well, there are definitely some similarities. So it seems that I'm on the right track with my model. Okay. I may not have refined it to the point where we'll call this a theory yet, okay? But I'm on the right track. I'm doing something correct. Okay? And what about this binary cosmic pretzel that we observed? Okay? Well, I couldn't quite form a pretzel, but I formed something similar. Okay, I did end up with a double disk around two stars. And what about this initial question I wanted to know? Can I form planets around binary star systems? And here is another model that I ran, okay, where we ended up with a double star system and planetary precursors. Okay, so over densities that will probably evolve into planetary bodies. Well, that's about all I have for you today. And of course, I'd like to acknowledge the University of Oregon and the National Science Foundation, for which I applied for a grant so I could go to graduate school, and they funded me. So, and all these other various entities that have helped me with my research so far. Now, are there any questions that I could answer?
I think we have one here. Do planets and stars form around the same time as each other?
It is believed that they form at the same time. Yep. So if we look now at these protoplanetary disks, okay, so this star and these planets that we believe are in these gaps are forming at the same time. Yes. So what kind of exoplanets were you guys looking at, you students looking at in class recently?
Oh, hello. I don't know if I'm allowed to talk, right? Just students aren't because they're recording. Yeah, we spent most of the time kind of focusing on stars. In normal years, we do go more in depth in exoplanets and planet formation, but in the sense of like looking at specific exoplanets, we didn't get too much into it. But we spent a lot of time talking about the life cycle of stars.
Okay.
And so I'm curious to if binary star systems, does that affect their life cycle at all in any ways? Like kind of like, I don't know, when it moves into the red giant. I know that's a little kind of off from what you were talking about. I'm curious about that.
It usually does. So it depends on the type of star system, a type of binary star system. There's a lot of sort of details about these systems that I glossed over, but there are two separate types of binary star systems we see, at least ones with planets, okay? But we see either wide separation binary systems, and these are more common than the very close binary star systems. Okay? So if you have an unequal mass pair of binary stars, and they're very close to each other, so in this close configuration, right? The higher mass will burn through its fuel faster, and it'll go into that red giant stage faster, right? And so when that happens, usually one star starts to pull from the envelope of the other star, okay? Or so they start to interact in that way. And this is actually how you can get a standard candle. So you'll get periodic supernovas from this type of binary star system. And the one star usually tends to always accrete the same amount of material. And so it goes supernova and gives off this very, very characteristic amount of energy that we can observe. And that helps us find distances in space. So yes, it does affect their life cycle, especially when they interact with each other. Great question.
Great. Thank you so much, Rebecca, for enlightening us on the star systems. I'm going to stop the recording now, and then we'll have an open chat if you'd like, and move into the raffle.
Okay, great.